the stream function. We have seen in previous section that even if the temperature is uncoupled from our system of equation of motion, we must solve the continuity and momentum equation simultaneously for pressure and velocity. The stream function psi, we have a definition for stream function in mechanical fluid. Psi is a clever device that allows us to satisfy the continuity equation and then solve the momentum equation directly for the single variable psi. Lines of constant psi are a streamline of the flow. Lines of constant psi are streamlines of the flow. The stream function idea works only if the continuity equation can be reduced to two terms. In general, we have four terms for the Cartesian continuity, for example. Continuity equation. In Cartesian and cylindrical. Equals to 0, and for cylindrical coordinate continuity equation stated as this relation. Equals to 0. At first, we can eliminate unsteady flows, and which is a peculiar and unrealistic application of the stream function idea. So we can reduce two functions in two terms, the most common application in incompressible flow in xy plane. Excuse me. So we have psi equals is a function of streamline satisfy identically if we had this relation for on plus equals to 0 comparison with the continuity equation, we can conclude that u equals to the derivation of streamline function by y, and b equals to derivation of the streamline by x. And we can write the velocity vector as the function of psi as this function. It is just a mathematical trick of replacing two variables by a single higher order function psi. A mathematical trick of replacing two variables by a single higher order function psi. Streamline. The vorticity or curve V is an interesting function. Vorticity can also have a definition for vorticity, which defined as curl V on the velocity vector and equals to gradient square of the streamline function, where the dou psi equals to the 2 order of the derivation of psi and is a scalar quantity. Thus, if we take the curl of momentum equation and utilize the equation of psi as right here, we obtain a single equation for psi for incompressible flow related to the momentum equation. So for a momentum equation, we can write curl of momentum This is the where nu equals to on rho is the kinematic viscosity. This is partly a victory and partly a defeat. In the equation of curl of momentum, we will obtain an scalar and has only one variable psi, but it now contains fourth order derivation and probably will require computer analysis. there will be 4 boundary conditions required on site. For example, for the flow of uniform stream in the x direction past a solid body, the 4 condition would be boundary condition. Let me 4 boundary condition. For example, for the flow of a uniform stream in the x direction past a solid body, right? A uniform stream in x direction past a solid body. At infinity, we have the 2 boundary condition for the streamline function equals to the velocity at the infinity and equals to 0. At the body, equals to 0. Many examples of numerical solution of the equation of curl of momentum and the boundary condition can be reached at the various references in the literature. One important application is implicit incompressible irrotational flow. Let me write implicit incompressible. Implicit means the viscosity equals to 0 in viscid incompressible irrotational. Equals to on equals to 0. This is the equation of for the continuity for the curve of V vorticity equals to 0. Let me write here vorticity. This is vorticity because it is irrotational flow. This is the second order Laplace equation. For which many solutions are available, and the boundary condition at infinity is the boundary condition at infinity. We have psi equals to plus constant, and at the body we have a boundary condition constant. The next subsection related to the streamline is geometric interpretation of a streamline function. Interpretation of streamline function. The fancy mathematics above would serve alone to make the stream function immortal and always useful to engineers. Even better, though, SAW has a beautiful geometric interpretation. Lines of constant size are streamlines of the flow. This can be shown as follows in the equation. We have the relation for the definition of a streamline in two-dimensional flow is, that was in the chapter 1 also, where we can calculate b dx or u dy minus b dx equals to 0. It is a streamline function. Introducing the streamline function from equation of the streamline, we said that the round u on round x, u equals to, and we had also this relation for the streamline. With replacing to the equation above, we can obtain this relation for the problem. It say that round plus equals to 0, it is this side. Thus the change in size is 0 along a streamline. The change of is 0 in the along a streamline. Or we can write psi equals to constant along a There is also a physical interpretation that relates psi to polymorph flow. Consider this picture. We can compute the volume of flow dq through an element ds of control surface of unit depth. dq equals to dA dot product to the unit vector, which is dy on ds minus j dx on ds multiplied to the a, which is ds multiplied to 1. As shown is the picture, we have the unit vector here and the velocity vector in this direction with the delta s, and the unit depth in the paper. So dq equals to thus the change in psi across the element is numerically equals to volume flow through the element. The volume flow between any two streamlines in the flow field is equal to change in stream function between those streamlines, and we have the integration of dq equals to q. We can write q from point 1 to point 2 in a flow. Further, the direction of flow can be ascertained by noting whether psi increases or decreases, as shown in the picture in the next page. So further, the direction of flow can be ascertained by noting whether psi increases or decreases, as expressed in this picture. The flow is the right if the psi u is greater to psi L, where the subscript stands for upper and lower and before, otherwise the flow is the left. Psi upper greater than lower the fluid flow in the right hand, and if not, the flow goes on the left hand. The next subsection is the steady plane compressible flow. Suppose now that the density is variable but the x direction velocity is 0. So in the case we have an variable. So that the flow is in the xy plane. Then the equation of continuity becomes we see that it is exactly the same form as the equation of continuity. Therefore, a compressible flow stream function can be defined as the relation of rho u equals to and if we consider that the function of a streamline the psi equals to 0, with comparing these two relations with the streamline function, we can obtain the relation for a compressible flow. Again, lines of constant size are streamlines of the flow, but the change in sign is now equals to mass flow, not the volume flow. So we have the relation and in the integration form we have, this is the continuity equation. The sign convection on the flow direction is the same as the streamline. This particularly streamline function combines density and velocity and must be substituted into only momentum, that but also the energy and state relation which stated in the for the energy equation with pressure and temperature as companion variables. Thus the compressible stream function not a great victory, and further assumption must be made to effect an analytical solution to typical problem. The next subsection in the streamline function is incompressible flow, plane flow in the polar coordinate. Suppose that the important coordinates are r and theta. In the polar coordinate, we have r and theta as variable in the polar coordinate with the mvz equals to 0, and that the density is constant. For plane flow in polar coordinate, then the continuity equation decreases to the two parts in polar coordinate. Equals to 0. After multiplying through by r, we see that this is the analogous form of the streamline function with this relation multiplied to r. We can obtain by comparison the two relation, these two relation, we produce the form of the incompressible polar coordinate stream function as Vr equals to and V theta equals to once again lines of constant psi are streamlines, and the change in sign is the volume flow. So we have also the volume flow for the definition, again changing the line of constant psi. Equals to streamlines, and the change in psi equals to the volume flow. The sign convection is the same as the previous figure. This type of the stream function is very useful in analyzes flow with the cylinders, vortices, source, and the sinks. Applicable in the analyzes flow in cylinders. Vortices, sources, and sinks. Analyzes this type of problem. The next subsection is incompressible axisymmetric flow. As the final example, suppose that the flow is three-dimensional, VR, VZ, but with no circumferential variation. So we have incompressible VR, V theta, and VR, VZ. Incompressible axisymmetric flow, V theta equals to 0. Such flow is a termed axisymmetric, and the flow pattern is the same when viewed on any meridional plane through the axis of revolution z. For incompressible flow, the equation of a streamline equals to, which is the continuity equation also. This is a type of polar cylindrical flow with the angular velocity equals to 0. This doesn't seem to work. Can't we get rid of the one r outside? But when we realize that r and z are independent coordinates, this relation can be rewritten as the function on z. We can obtain also it comparing these two relations with the psi function. We have this. We can obtain this relation for the continuity as a function of streamline. VR equals to and VZ equals to here again we have a constant of psi streamline, but there is a factor 2 pi in the volume form. In this case, to calculate the volume flow, two pi the sign convection on the flow is the same in the previous picture, that u psi u greater than psi L, the flow is in the right hand side, and also vice versa.